cover all the things that we need for this course, but maybe it's too much, so maybe we'll have to do another class about this topic. Okay, so first of all, well, there are some things that I won't define, like abelian category, sheaves, functors, left exact functors, and so on. So, well, if there is something that I mention and you don't know what's the definition, you can ask. Okay. So let A be an abelian category. So an object I of the category is said to be injective if for every monomorphism and every morphism there exists a morphism extending it. So we have here injection, we have the morphism to the injective object, and there exists this extension that makes this diagram commutative. Okay. Okay, so it's easy to check. In particular, sums, direct sums of injective objects are injective. Okay, and we say that the category A has enough injectives if every object is a sub-object of an injective. If for every A there exists a monomorphism with okay. Well, I think that today we will not get to the point to talk about any category, I mean any special category. But well, later we will see examples of how to construct injective objects in certain categories. Okay, and examples of categories that have enough injectives. Okay. So definition. So let F from A to B be a left exact covariant functor between abelian categories with A having enough injectives okay, and let AD be a complex, a left bounded complex of objects of A. Okay. Okay, so assuming, well, I will going to assume there exists another complex I D complex of injective objects of A, and there exists a morphism of complexes. So I will write it just like this. An alpha dot such that it is a morphism of complexes, and alpha k is a monomorphism for every k less bigger or equal than 0. Okay, this is left bounded. Okay, this is a morphism for every k, and furthermore, alpha dot is a quasi-isomorphism. And this means that the induced mapping cohomology, so the HK of alpha dot, that is a morphism between the HK cohomology group of alpha of A, of the complex A, to the HK cohomology group of the complex I. This is an isomorphism for every K. Okay, so suppose we have all these things, then I don't know if to put it here. We define, no, maybe we'll put it there. Okay, then we define the kth derived object of A dot with respect to functor f as the following object Rk f of a dot is defined to be, well, up to isomorphism as the kth cohomology object of the functor applied to I dot. Okay? So it's clear the definition. I mean, I haven't proved that it is well defined. But do you understand every name that appears in the definition? I mean, quasi. Understand what I mean by complex, by left-bounded complex? Yes?
What is a left-bounded complex?
Left-bounded complex means that it's 0 for all the negative indexes. Okay, it starts from A0, and before that you have just 0, the 0 map. Okay? And okay, so everything is clear. Monomorphism, all that stuff, I don't have to explain it. Okay? Cool. Okay, so this is the derived object. And today class we will spend the whole class probably in order to prove that this object is well defined. And if we get to that, we will prove that in fact it is well defined in the derived category, right? So it's defined up to quasi-isomorphism. Okay. Okay. Everything fine? Yes? No? I don't know. Okay, so proposition 1. The kth derived object is well defined. With this I mean if we choose another quasi-isomorphism to another complex of injectives object such that the complex's morphism it's a monomorphism at every degree, then there exists a canonical isomorphism between hk of fi and hk of fj. Okay. Okay, so in order to prove this proposition, I have to recall a definition. So let phi and psi being two morphisms of complexes, isomorphisms of complexes in an abelian category. We say that they are homotopic. Oh, no. A homotopy between phi and psi is a collection of morphisms hk from b from a k to b k minus 1 such that h k plus 1 composed with d. So here I am assuming that the differential map here is always d plus d composed with hk is equal to phi k minus psi k for every k. Okay? So in particular, whenever we have an homotopy between two morphisms of complexes, the induced map in cohomology is the same. So in particular, hk of phi dot is equal to hk of psi dot. Okay? And this is trivial just by looking at this equation, right? Okay. So lemma 1. Let alpha and beta. Okay, consider two morphisms of complexes as B2 quasi-isomorphisms I think I don't need them to be quasi-isomorphisms. Wait 1 second. Alpha. I think I just need alpha to be a quasi-isomorphism. Okay. The two morphisms of complexes such that alpha dot is a quasi-isomorphism and alpha k is a monomorphism for every k. Well, from now on, I will always use left-bounded complexes. So whenever I say a complex, I am meaning a left-bounded complex. Okay. So if I forget to mention it, I don't want to put it all the time. Okay. So assume that alpha k is injective for every k. Well, here this is the notation I am using. Okay. Maybe I will forget to mention that in some other point. And when I put this hook arrow, I mean that. Okay. So you have these two conditions, and the j k is injective for every k. Okay. So then, for every morphism of complexes phi from A to B, there exists a morphism psi from I to J, such that we have the following commutative diagram. This commutes, and psi is unique up to homotopy. Homotopy equivalence. Well, homotopy. Okay, it's clear. Everything is clear. The lemma is clear. Is the lemma clear? Yes. Okay, so proof. Okay, first of all, what we have to do is to construct this map, this psi. We have to construct psi, right? And after that, we have to prove the uniqueness up to homotopy, right? So for the existence, in order to construct psi dot, so psi 0 is just given by the definition of being injective, right? I mean, we have this diagram. And since we know that J0 is injective, there exists this phi 0, okay? So this is quite simple. So now, so suppose now, I don't know how to write this. Assume we have constructed let's say psi 0 up to some psi k, such that each of these psi I satisfies that, well, we have the commutativity of the diagram that we're looking for. Right, and I will also ask it to be a morphism of complexes, right? So we also have this property, right? Okay. So assume we have these two properties that are satisfied by the phi k's we have already constructed. So we have to construct phi k plus 1, right? Okay, so how will we do this? Okay, so consider the morphism so what's the morphism? D plus alpha to the k plus 1 that goes from I to the k plus a to the k plus 1 to I k plus 1. Okay? So consider this morphism. So since alpha dot is a quasi-isomorphism, we have that the kernel of this map is equal to the image of the following map, alpha k minus d, where this alpha k minus d goes from ik to ik, goes from ik, to ik plus 1. Right? Here you have to use that alpha dot is the quasi-isomorphism. You can check it. I mean, it's easier to check this in the case of abelian groups. I mean, when you have elements, right? When you have elements, this is elementary. Okay. Do you want me to check that? I mean, so if you take an element here that goes to 0, right? You will have that the image of this element under alpha k plus 1 will be the exact, right? So it will be 0 in the cohomology of I, right? So since alpha is a quasi-isomorphism, the image of this, well, I don't want to write this down, okay, but it's super simple exercise, okay? Okay, so we know this. We know that this is the image of this map is the kernel of this other map, and so we consider now the following morphism psi to be decomposed with this is about bar phi, I don't know, lambda decomposed with psi k plus beta k plus 1 composed with phi k plus 1 from ik plus I a k plus 1 to jk plus 1. Okay, so if we consider this morphism, we see that lambda of this other morphism composed with alpha k minus d is what is exactly d composed with phi k composed with alpha k minus beta k plus 1 composed with phi k plus 1 composed with d, right? And by construction, we know that this d is commuting with whenever it commutes with phi, you will get psi, right? And whenever it commutes with beta, you will get alpha, right? So, I mean, this is just the commutativity assumption, right? So this is 0, right? And so this map factors through the through the image of this map, right? So we get another map. I will write this diagram. So the image so here we have the image. This is injected inside ik plus 1, right? And we had this map from here to jk plus 1, right? This is lambda. And we have an induced map here, lambda bar, right? And we're done, right? We just extend this map using the injectivity of jk, right? So there exists this psi k plus 1, right? And just by this diagram, it's clear that you will have so that satisfies in the following properties. So if you take here something and 0, you will go here from D and then phi k plus 1. So you will have that phi k plus 1 composed with D is the same thing as the first coordinate of lambda, right? The first part of lambda is D composed with phi k. And on the other side, you will have alpha k plus 1 composed with psi k plus 1. And this will be the same thing as this beta k plus 1 composed with phi k plus 1, right? Okay, so this finish, I mean, like the inductive construction of phi k. So we proved the existence of phi k, of the phi dot, right, of this map. So now we have to prove that it is unique up to homotopy. So for the uniqueness, let phi tilde dot be another map satisfying also the same hypothesis from beta, which is okay. So we have to construct this homotopy. I mean, no, it's from I to J. Okay, so we will construct the homotopy. Okay, so let H0 define it as 0, and assume that we have constructed H0 up to HK such that, so this HK will be from IK to JK minus 1, such that HK composed with D is equal to, well, yeah, it's equal to, well, plus D composed to HK minus 1 is equal to phi K minus 1 minus psi tilde K minus 1. And also, we are assuming that hk composed with alpha is 0. Okay? So take the map. What's the map? Mu phi psi k minus psi tilde k minus d composed with hk, comma 0. I mean plus 0. This plus 0. And this goes from ik plus ak plus 1 to jk. Okay, so again, since mu of this other map alpha k minus d is equal to what? This is psi k composed with alpha k minus psi k tile composed with alpha k, and this other map, this thing will vanish. This is 0. Then we have an induced map, right? Then, well, this and the fact that I mentioned before, right? The kernel of this map, e plus ik plus 1 is equal to the image of this other map, alpha k minus d, right? So we have the following diagram. We obtain the following diagram. So again, here we have ik plus ak plus 1 goes to its image under this map, d plus ik plus 1, and here we have this other map mu to jk. It factors through the image, and this is inside ik, and so I mean k plus 1, and so we can produce this hk plus 1 using the injectivity of jk. Okay, and again by the way we constructed, we check that it satisfies. So the first coordinate of mu will be phi k minus phi tilde k minus d composed with hk, and it will be equal to d composed with hk plus 1. And the second coordinate of mu is 0, so we will get that hk plus 1 composed with alpha k plus 1 is 0. Okay, and this is the proof. Clear? Yes? Okay, so with this lemma we can prove proposition 1. So proof of proposition 1. Okay. So by lemma 1, we have two maps, right? We have a map psi dot from I dot to j dot, phi dot and psi dot. We have two maps, right? And we know, and so we can compose them, right? And so we have this psi dot composed with phi dot psi dot, I mean phi dot composed with psi dot, composed with beta dot, I think. Yes, is equal to beta dot, and this psi dot composed with phi dot composed with alpha dot is equal to alpha dot, right? And so, since this relation also is true for the identity map on the complex, the lemma 1 will imply that these two compositions are homotopic to the identities, right? So then this is homotopic to the identity. So it goes to the identity of J dot, and this other one is homotopic to the identity of I dot. And so the cohomologies, the induced cohomologies are the same, right? I mean, and so, well, this F composed with this is homotopic to this. And F of psi dot composed with F of phi dot is homotopic to this other map, and so then the HK of F of psi is equal to HK of F of psi dot inverse, right? And this gives you the isomorphism. Right? Okay. Okay, so we have proved that the derived functor is well defined, right? I mean, but we haven't proved that every object, I mean every complex, have a derived functor, a derived object, right? So, but it's easy to see that there are some kind of complexes that have derived objects easily, right? So I will define it here. So definition, let A be an abelian category with enough injectives Okay, so we define the derived object of an object. So for every A, an object of A, its kth derived object under F. So I'm assuming F is a left exact functor, covariant functor. Between abelian categories. Okay, so by definition, we define it as the following thing: Rk of F of A is by definition Rk of F of A dot where A0 is defined to be A, and all the others are 0. Okay? So in particular, in order to prove that we can compute the derived object of A, we just need to produce a quasi-isomorphism between this complex, right, and a complex of injectives objects, such that it's an injection at every point, I mean, in every degree, right? But that's exactly the same thing as the following. So what we are doing is taking here the complex A dot, right, that it's 0, A, 0, 0, and so on, right? And we have to produce here an injection into some I0, right? And here, well, all this map will be injective, right? And here we have to take A1, I1, I2, and so on. And what we need is this to be a quasi-isomorphism, right? So obviously all the cohomologies at every level except this one will be 0, right? So what we're asking is that this complex must be exact everywhere, right? And here, the kernel of this map has to be equal to the kernel of this map. I mean, it has to be A, right? So this is exactly the same thing as saying that this left-bounded complex is a resolution of this object, right? This is equivalent to say that this is an injective resolution of A, right? So in order to prove that every object admits a case-derived object under F, we just need to prove that every object in an abelian category with enough injectives always admits an injective resolution, right? Right? Yes? And this is trivial, right? And this is the only thing that you have to do is to take the cokernel of the map ik minus 1 to ik and extend it by an injective at each step, right? You start extending A with some I0, and then you take the cokernel of this map, and so on, and you go extending. Clear? Yes? Okay, so we say that A is F acyclic if all its derived functors are 0 for every k bigger than 0. Okay? Obviously, the R0 of FA must be FA, right? Okay. And in particular, every injective object is F acyclic. F acyclic for every F. right? That's obvious, right? I mean, its injective resolution, it's given by itself. Okay, so now we will prove that in fact we can produce this derived object not only for complexes of this form, but for every complex. Okay? This is a little bit more difficult. So, proposition 2. For every left-bounded complex A dot on A, well, abelian category with enough injectives. So let's see, with enough injectives. There exists a complex I dot of injectives and a monomorphism A dot into I dot alpha dot, that it's injective, that is monomorphism for every k. That is a quasi-isomorphism. Right? This is what we need in order to prove that we can define the derived objects. Okay, so in order to prove this proposition, we will have to use several lemmas. Okay, so lemma 2. So for every object, for every complex, A dot, there exists a complex of injectives extending it. Okay? So here we have this alpha dot, and all these alpha k's are monomorphisms. Right? Okay, so the proof. Take any I0, right? Alpha 0 into something I0, into some I0 injective, right? And now we will construct the others. So first, let's construct I1. And its morphism. So consider the following diagram. So we have here A0 that goes to the map to, let's say, D, that goes to A1. Here we have, well, I will change the name of this. I will put it I dot I0 to I0. And here we want to produce some I1 that fits in this diagram, right? So how do we produce this guy? So consider the following map. So the natural injection of I0 in its direct sum I0 plus A1, right? We have this other injection here. And here we will take the induced map in the coproduct, but the induced map will be I0 and minus D. Okay? So this part is not commutative. Okay? And so now take the following map that goes from I0 plus A1 to the cokernel of this map of I0 minus D, right? And then take any injective extending it, I1. Okay? Okay, so remember that this part is not necessarily, this part is not commutative, right? But this part is, right? And now take, let's call it D, bigger D, to be this map. Okay? I don't have space. Right, and so, and this will be a I1. Right, so first of all, we have to check that this map is injective, right, from A1 to I1. How do we check that? So, so assume that you have some element here in A1 that goes to 0 there, right? That means that it went to 0 here in the cokernel, right? That means that it's coming from here, from A0, under this map, via this map, right? But this guy here goes to 0, comma, the element, right? 0A. And it's coming from something here, right? And this part is commutative. So the image of this part here will be necessarily 0 because it goes to the same image that an element here, right? So since it will be 0 here and this map is injective, that means that this guy here is 0, right? So its image here is 0. And since this other map is also injective, that implies that it was originally 0 here, right? So this map is injective, right? And this diagram is commutative. Okay. So and so we produce this first morphism D from I0 to I1, and it satisfies the following property. And it's easy to check. That we have the following relation, that the kernel of this composition from A1 to I1, this I1, composed with the projection to the cokernel of D, this is equal to the image of D from A0 to I1. Right? How do we check that? So again, okay, let's assume that we have an element here that goes to 0 here in the composition with the cokernel, right? Okay, so you have an element here that goes to 0 here. That means that this element in here comes from something here in I0, right? So that implies that there exists some element here that its image in I1 is equal to the image of this element coming from A1, right? So if you take the image, well, let's put it a name. So let's say that here we have an X, and let's say that here we have a Y. Okay? So Y here will go to Y0, right? And X here will go to X0. I mean 0x. right? And we know that they go to the same thing here in I1. So in particular, they go to the same thing here in the cokernel. So the difference will be y minus x goes to 0 in the cokernel. So it comes from here, right? So there exists some z here such that the image of z inside I0 is y, and the image of z inside A1 is x, right? So x exactly is in the image of this map, D. This is what I claimed, right? So you take an element here, and I prove that it was here in the image, right? So and in the other direction, so if you have here an element, you take x here, and you have an element z here that goes to x, right? So this z will go to something here, a y, and then the image of x that will be 0x will be equal to the image of y that will be y0 up to the image of this map. I mean, when you take the difference and you compose them with these two maps, you will get to the same element, right? So the image of so x will go here to 0x, and here will go to the same thing, that taking y and y0 and all this stuff. So since it's coming from D, when you pass to the cokernel of D, it will give you 0. So the image of x under this composition will be 0, right? So this equality is true. Okay. Okay, so we have this property for the D, the first D that we have constructed. So now assume we have already constructed so D from ik minus 1 to ik, such that we have also this ak minus 1, ik minus 1, d ak, ik, right? So this commutes, and also we have the analog of this property, right? So we also have that the kernel of the map that goes from ik to ik, and then to the cokernel of D is equal to the image of D from ak minus 1 to ak. Okay? Okay, so now we will construct the ik plus 1 with its morphisms. So we construct the following diagram. So again, we have this ak minus 1, d to ak, this inside ik minus 1, big D ik, this inside this, ik minus 1, ik. Okay, and so we have here D ak plus 1. And we have to complete this diagram, right? So how we will do it? So first of all, we take here the cokernel of D, of this D. Okay, and again, we put this inside the direct sum of the cokernel of D with ak plus 1. So we have here the injection, and we have here the following induced map. So it is ik comma minus D, right? Again, this part is not commutative. And so you take this, and now you compose it with the cokernel. You project into the cokernel of this map, ik minus D, and then you inject this into some I k plus 1. Okay? And so this will be your next D. Right? Okay, and we have to check that this, well, this satisfies all the properties that we want. Okay, and this will be the map here, ik plus 1. Okay, so first of all, we have to check that this is injective. This map must be injective. Okay, so let's take elements. Let's do this count. So take here any x, right? And assume that it goes to 0 here. Right? So since this map is injective, this means that it goes to 0 here. Right? And so that means that here it comes from this map. Right? So here it's 0x. And, well, not necessarily comes from this map. This means that in the co-kernel it's 0. Right? So that means that here there is some y that goes here to some, let's say, y again, that goes here to something. It injects here. Let's say here it goes to z, and it goes here to c, x, and we know that the difference of these two guys in the co-kernel is 0. Right? So that implies that d of y must be x. Right? D of y must be x, and so maybe confused here. No, I proved that this map comes from here, right? And this goes to x 0x. This implies that x is 0, right? Okay, I'm confused. Well, I think it's, yeah, it's come from here, right? So it will be d, it will be the d of y, and ik of y will be 0, right? So that means that z here is 0, right? So y composed with the ik of y projected into the co-kernel is 0, right? But we know that the kernel of this composition is the image of this map. Right? This the hypothesis we are adding to the inductive construction. So this means that there exists here something, I don't know, omega, that goes to y, and y goes to x. So this is a complex. This means that x is 0. Right? So this map is injective. Okay. Well, and you also have to check the following thing. You have to check, so ik plus 1 is injective. And also you have to check that the kernel of the composition of this map, ak plus 1 to ik plus 1, projected into the co-kernel of D, must be equal to the image of D from ak to ik plus 1 to ak plus 1, right? Well, this is something that it's almost the same diagram that we have in the case 1, so I won't do again this count. And well, and the other thing that you have to check is that D composed with D is 0, right? The big D composed with D is 0, but that's obvious, right? Because it's factored by the co-kernel of the first D, right? It has this, and D composed with this, right? And so this is the proof. Okay. I don't know what time is it. Okay, now let's another lemma. So lemma 3. So let I dot dot d1 d2 be a double complex, a left-bounded double complex such that and let A dot be a left-bounded complex such that there exists a morphism of complexes, I don't know, alpha dot, that it's injective for every k. Okay, and such that alpha p from AP inside IP dot is a resolution of A P for every P. Okay. So let all this, assume all this. So now defining the simple complex associated to the double complex. So we will define this Ik as the direct sum P plus Q equal to K of I PQ. So we have this is the object and the morphism. So maybe I will put the simple complex here. I dot big D, and we will define so big D from I PQ to I K plus 1 is defined as so I will define it like this: minus 1 to the Q D1 plus D2. Okay. So it's easy to check that this is a complex. I mean, D composed with D will be 0. Okay, I won't do that count. So defining this simple complex associated to the double complex, there is a natural injection of the complex A in this simple complex. So the injection of A inside I is a quasi-isomorphism. Okay? So using this lemma, what we have to do in order to produce a complex of injectives that will allow us to compute the case-derived object of this complex is we will first construct a double complex, and from this double complex we will construct this simple complex that will give you the quasi-isomorphism that you're looking for, right? Okay, so the proof of this is quite simple. I won't do it. So so the proof is something like this. You will have here your complex A, right? A0, A1, A2. Maybe we'll have to write it like this. Oh, well, I will put it here. Okay. So the proof is quite simple. So you have here this injection into the 0 level, right? I0, 0, I1, 0, I2, 0, and so on. And then we have that these maps, the horizontal maps, they are all resolutions, right? Okay, so now what's an object of the simple complex associated to this double complex? So it's an element that is taking like each one element of one of these diagonals, right? So you take it here, an element here, other here, another here. So let's, I don't know, x, y, z. And we know that this big D applied to this is 0. What does that mean? That means that the D2 here, D2 of this guy will be 0, right? And the D1 will cancel with the D2 of y, right? And the D1 of y will cancel with the D2 of x, and the D1 of x will be 0, right? That's the property, more or less. So what we have to do is to use that the rows are injective, right? I mean, are exact. We know that every row is exact, right? This is the hypothesis of the proposition. So since this is exact and this goes to 0, there exists some other guy here that goes to it. And then it's D, the big D applied to this guy. We can subtract it to here, right? And so it will be in the cohomology of the whole simple complex associated to this double complex. They will be the same. I mean, the image of this guy here of omega, the big D of omega will be 0 in the cohomology of this complex, of the simple complex, right? So if we subtract it, we will obtain the same element in the cohomology of the simple complex, right? So we can assume that this guy is 0, and then we can do the same thing to this guy. I mean, if this is 0, we know then that the D2 of this guy must be 0. And so we can do the same procedure again, right? We can subtract something from here, and at the end, what we will get a representative in the cohomology that comes from here, that it's just an element of here that goes to 0 upstairs and by D2. And so it's in the kernel of D2. But the kernel of D2 is the image of A2. is A2 because it is it's an injection, right? So in particular, this object will represent an element of A2 that goes to 0 here, right? So it's representing an element in the cohomology associated to the complex A, right? So that's how you produce the inverse of the map associated to this map in cohomology, right? You have to produce the quasi-isomorphism, and I have just explained you how to produce the inverse of this map, right? And that's how you prove that this is an isomorphism. Okay? So we have this other lemma, and then we are done, right? With the proposition 2. So the proof of proposition 2 now is trivial, right? Okay, so using lemma 2, produce this double complex, right? I mean, we produce first this one and then complete the exact sequence, right? And so on, right? At each step, we're taking, this is D2. We're taking we're injecting the cokernel of this inside this, okay? And then we use lemma, and then use lemma 3. Okay, and note that the direct sum of injectives is injective, right? Okay, clear? What time is it? I don't know what time is it. Okay, so I think that, let's see, lemma 4. Okay, I will state a lemma here. I don't know if I will prove it. Maybe I will. No, I think that I have to prove it. Okay, I will prove it next class, okay? But okay, proposition 3. So let A be an abelian category with enough injectives and alpha from A dot to B dot via quasi-isomorphism of left-bounded complexes. Then the derived objects are isomorphic. Yeah, this means that the derived object is something defined up to quasi-isomorphism, right? So this is saying that it's defined in the derived category of A, in there plus A. Okay, so in order to prove this proposition, I have to prove first a lemma. So let's say lemma 4. So let alpha from A to I be a quasi-isomorphism of left-bounded complex, where all these I dots with these ik injectives for all k, then the Rk f of A dot is isomorphic to the cohomology of f of I dot. Okay, so using this lemma, this proposition is trivial, right? So proof of the proposition. So just take a quasi-isomorphism B beta to some complex of injective elements, right, that satisfy all the properties in order to define the derived objects of B dot. And we know that it exists by way proving proposition 2. So take any of these guys, then this alpha dot composed with beta dot is a quasi-isomorphism. And so the Rk of f of A dot is isomorphic to the kth homology of f of I dot, and this is by definition isomorphic to Rk of f of B dot, right? So the point is to prove this lemma, lemma 4. And I don't know what time is it. Okay, I will leave the proof of lemma 4 for the next class. And now I will just finish the class with the last proposition. Proposition 4. So again, in the same hypothesis as always, let alpha dot from A dot to B dot be a quasi-isomorphism such that and assume Bk is f acyclic for every k. Then we can compute the kth derived object using the quasi-isomorphism with B. Okay, this is what we will use in order to compute all these things. Okay, this is the main proposition of the class. And how is the proof? So the proof. So again, by the previous proposition, it is enough to prove that. So it is enough. It is enough to prove that the Rk of f of B dot is isomorphic to Hk of f of B dot. Right? And so we know that we can construct by the proof of proposition 2, we can construct this double complex IPQ of injectives, right? Such that BP inside I P dot is a resolution for every P. Right? And so since we know that the BP is acyclic, F acyclic, this means that when we apply F to this long exact sequence, it will remain exact. Right? So this implies, since BP is F acyclic, this implies that this is a resolution for every P. Right? And now we can apply lemma 3. And now we can apply lemma 3 to the double complex F of I dot dot. Right? And so by lemma 3, by lemma 3, we know that this is this is a quasi-isomorphism. And so we know that the cohomologies are the same. And so HK of F B dot is isomorphic to HK of F I dot, but this is the K derived object of B dot. Right? And so we're done. Well, a corollary of this is that every left-bounded exact sequence of acyclic objects remains exact when you apply F, right? So corollary. Right, and this is just because it will be quasi-isomorphic to the zero complex, right? And so the derived object of the zero complex will be isomorphic to the cohomology of F applied to the acyclic exact sequence, right? And so the cohomology of the sequence obtained after applying F will be zero, so it will be exact. Right. Okay, so we will continue next class.